Okay, welcome back, everybody. Our next speaker is Felix, whom you already met in the panel. He will talk about from the life of a data scientist.
Thank you. So I have the pleasure to continue with the discussion of the panel, and this time alone. So this is good. So there will be no other opinions. No, I'm joking. So it will be a quite long talk with touching quite a few different topics. So just ask in between is best, because afterwards it might be you might not remember everything. So short outline of what I'm going to talk about. So in the beginning, I will introduce a few buzzwords, which all of you already know, of course, but still to see how I would define them. And then most of the talk will be about a definition of, or a trial of a definition what data science could be, or at least how it is for me when I work as a data scientist. And then in the end, a few short real-world examples where we did customer projects involving data science to give you kind of an imagination how it works out there. Okay, so I begin with this famous hype cycle of Gartner, so which probably all of you already know. So the scientists maybe not, but so you probably cannot read what is written there. But basically, what it means is that each year Gartner publishes a list of these buzzwords, which are just hip at that time, and estimates the time how long it takes until they become standard. And standard means that they are actually used with some, let's say, business value out there. And what you see on the right side of the plot, so the small plot, so this is just how it usually behaves, such a hype cycle. So there's a technology trigger in the beginning, and then such a buzzword is really hyped, and it goes up to this peak, and then usually it falls down into the trough of disillusionment, and then afterwards it goes up to until it's really in production and you can use it productively. And here you see the oops. It wasn't me. Here you can see some words which are interesting for our topic. So this means data science and prescriptive analytics here. So I will go through those. Internet of Things, you already heard in the panel discussion, which is just hyped at the moment, and big data, which is already on the way down to the trough of disillusionment. So, and here's a comparison between the last 2 years. So you see the blue cycles, there is big data, so which was just on the peak and is now going down. And the time for it is relatively long, so it's 5 to 10 years. And what is there in red is the time for predictive analytics. So predictive analytics went through relatively quickly, so it's only 2 years. So that means actually, this was something which was better defined than big data. So you can really say what predictive analytics is. With big data, it's much more difficult to define what you actually mean with it. So, but I will start with that. Try to give at least an explanation what it means for me. And basically, it's just the data which comes from all the different kind of industries and economies. So there might be something from stock exchange, which you can use to try to give some forecast there, which is usually pretty difficult. But you could earn a lot of money with it, of course. Then we heard about banking and insurance, which is difficult because of data security in Europe. Retail, which I said in the discussion already, is something which we have done a lot in the past. So there you can do kind like replenishment and demand forecasts, dynamic pricing, and so on, which is also true for online shops. Location-based services might be something which could be interesting in the future. So you saw yesterday an interesting talk about the cars. So this was something which you see there are some applications of it. And then, of course, production and industry, which I already mentioned, which will be in future maybe one of the biggest things to come with the Internet of Things, and with really the possibility to store and process this whole large data set which are there. So then predictive analytics, which I said, which is something which is more or a bit easier to define. So actually what is written there is that analytics are no longer a nice to have. So what I mean with that is basically in the past, what was there is this descriptive analytics. So this is there for tens of years. So this is basically business intelligence. So that means drill down stuff. You can see what happened. You can maybe get an idea what you could do, but there is no real action from it. There are no forecasts. Yeah, if you really go to it, why did it happen? So you get an idea about your business, then you would call it more like diagnostic analytics maybe. And then if you go to just from this information to do an actual forecast, then you would come to this terms predictive and prescriptive analytics. So predictive analytics is basically what you would define as machine learning, so that you do actual forecasts for some target variable, and then with just these forecasts, the customers usually cannot do too much, so they would need people on their side which can get some value out of it. So that means usually what is better if you already deliver decisions to the customer, and this would mean prescriptive analytics. So here I write it, how can we make it happen? So this just means you give the customer already his business case at hand and not just numbers, which will have no use maybe in the end. So this is basically what you would like to have. So you have on customer side maybe a controller, and then the data is delivered from the customer. So here it's now in the cloud. So this would mean, so our model more or less is that we do it as in our own platform. So the customers deliver us the data via a defined API, and then we run all the stuff on our side and deliver decisions and actions back. So another model would be what we also heard yesterday. Most of the customers maybe would like to have it on-premise more. So in industry or banking or such things, so this is usually the case. So then you can maybe just leave out the cloud and see it as a service on there. This works exactly the same way. So you have a defined data delivery, then you have your predictive application and send the decisions and actions back. And then there might be a controller which decides what to do with the decisions, or you have it completely automated, which might be the way to go in future. And of course, you can also use external factors which are not in the data delivered by the customer. So this might be something like weather data, economic indices, or whatever. So, and this is of course something which is then which has to be done in the predictive application, that you just include all these different data informations and build a model out of it. So then I come to the central term data science. So this is now something which we heard it already, that is quite difficult to define. And so I would say all the stuff which we discussed there is that one said that it's basically just model development, so that data scientists dealing with statistics, dealing with machine learning. And another one said it's all about engineering. So, and actually, both is true, I would say. So a data scientist has to do all these things. So it is all about engineering. That's true. So there is no data scientists which who has no coding skills, I would say. So this will not work. So a data scientist is basically a software engineer, but it's also necessary that you have some background in statistics and machine learning, that you really understand the stuff. So that means this predictive modeling and machine learning and statistics, what I said there with causality is also coming to statistics. I will explain it a bit. And also data exploration means you have to know what you are doing. You have to have the skills to really explore the data. That means in Python you have to know the libraries. You have to have the ability to code. And what comes then there additionally is the business development and data storytelling part. So that means that usually you also have to deal with the customer. So there might be some data scientists which are only maybe doing the development inside a larger company and have their own project manager or somebody who does this stuff. But usually I would say the data scientist should be able to tell the outcome also to the customer. And also develop a kind of a business case. So this also belongs to the duties of the data scientist. And the large point, which is there just on the left side, which you cannot read that good, I guess. So this is then also a bit about operations. So data science, in that sense, that it makes a business value means that you're not building just a model and then, as we heard yesterday, it goes to PowerPoint to die. So, but it means that you have a model which is actually running productively in the end, and which is then used, and you have to find a way to define the infrastructure, to have the data access working, to have a solution for storage, and so on and so on. So all this belongs also to the duty. So you have to know a lot of things, actually, and there are a lot of topics to cover. And this is basically what a data scientist do. So I will now give a few more details to some of these points, and I will mostly concentrate on the machine learning and statistic point, because there might also be some people out there which are not from science. For the others, it might be a bit maybe boring, but anyway. So basically, what has to be said? Why do we do it with statistics? So, and this is because there are two extremes. And the one is there's complete randomness. So this might be something like lottery, so where you cannot say anything. So one would say deterministic chaos or something like that. And the other thing would be you can just calculate everything. There's just causal effects, and you know the outcome, like in mechanics or for a pendulum or something. But the reality in business is usually something in between. So you have a part which is actually non-random, which you can calculate, which might be something like expertise knowledge or domain knowledge or something, and you usually have to extract this and exploit it. So you should not include that stuff in your model. So you just have to know your use case, have to extract this thing, and then exploit the correlated pattern in the data just by your machine learning models, so by your statistical models. And this is basically what you should do. So coming shortly to statistics. So what's the probability for head or tail in such an experiment? Usually, for a frequentistic approach, you would just have to try it very often. And then you need a lot of experiments, and then you can decide what the probability is. So, but this is not reality usually. So there you have only one trial, or you don't know in beforehand what it will be. So you need kind of a different ansatz to solve such things. And what you could do is, for example, Bayesian statistics. So this is there you have a prior knowledge, which I have notated there with on the right hand side. So, and this basically includes the information you have before. So I will come to it in more detail. Then you have this likelihood, which is basically what you optimize. So this is what you would use which you would minimize in your likelihood method or whatever. So, and then in the end, you are interested in the prediction. So that means the hypothesis under the condition of the data which you actually have. And the data in the denominator is just for normalization, actually. So this isn't changing in the process. So, and by this, so what is interesting there is the prior. So, and the question is where to get the prior from. And this can then be, for example, historic data, so that you know something from your business beforehand, which you could use, some statistics or something. It can be some properties of the system. So for our coin experiment, it would be just that you know that both sides of your coin are equal. It can be experience, or what I already said, expert or domain knowledge. So this is mostly very interesting, and you can just include it in your model by this methodology of Bayesian statistics. And just a remark there, if you know nothing about it, then if you know further information is there, then what you often take is a uniform prior, which is actually not the best thing to do. So actually low digits are more frequent than high digits, and this is what you see there. So this is just a statistical fact, so just good to know. So this is something, basically everything I would like to say to basic statistics. So, but what is nice to know additionally is correlation versus causality. So this is something which was discussed in the past quite a few times, and you see there a paper where it was mentioned that basically causality is dead. So actually scientists know that that you should not draw the a conclusion simply on the basis of correlation, because you have to extract the causal effects beforehand. But one could think that if you have really big data, you could do everything with correlations. But actually, this is not completely true. So it's not always sufficient. So it might be okay in most use cases that you just go without any thinking to your problem, just put it into a machine learning model and think that everything works out. But in reality, there are actually many use cases where you have to maybe do some decisions which are then changing the behavior of your model. So that means that in this case, X and Y can be just correlated, but there can also be some causal influence from one side on the other. So there on the right-hand side, so X causally influence Y, but not the other direction. And this can be an interesting information for a model. So for example, relevant for business cases would be, for example, dynamic pricing. So if you have an online shop and you can decide what the price of an item should be, and what you want to optimize is the revenue in the end. So that means your target would be the revenue. You have some historic data, which are all your features you have from your shop, and you have an action which you can do. So that means you can change the price, and by changing the price, you are actually changing your model in the end. So you are changing the whole behavior of the system. So, and for that, you cannot just say that the causal effects have no influence, and you can actually exploit that fact. So, for example, if you think on promotions, for example, catalog sending, so that means you would have a customer which sends out catalogs, and then hopes that the revenue for the customers who get a catalog is increased. And for that, it's very important to really take into account the politics in the past, for example. So which customers got the catalog in the past? Is it better to send somebody a catalog or not? So maybe somebody is spending money anyway, then you shouldn't waste money on your marketing stuff. Maybe it's there are few customers which haven't spent much in the past, but should get a catalog, and then they would buy something. And for that, you could use such an effect inside your machine learning model and could just exploit this. So this is then really going into the direction of reinforcement learning also, and this can be an interesting topic. And actually, we have done quite a few projects doing that stuff. So then to the next point, very shortly, data exploration. So we heard already quite a bit about it, and everybody said, okay, most of data science is just about transferring the data, doing your pre-processing, knowing the features, dive into data, visualize them, and so on. And this is actually true. So most of the work is really done there. So in your models, most of the data scientists are not really developing, let's say, machine learning models like an advanced support vector machine or something. So they are actually working with the data. So what you need to have is you need to have some good models which are working for you to understand what correlations are in the data, and to understand what happens to it, how they are correlated to each other, what would be interesting, what is the correlation to the target, and so on. This means you usually should do also such two-dimensional distributions. So you should check how the different variables behave. You can do this with profile plot, heat maps, or whatever. So one example would be something like this. So here are on the two axes are just your features, so the same on both axes, and you see always the profile plot of one feature versus the other. And on the diagonal, you would see the profile plot to the target. And by doing something like that, you can learn something about your data set. And also, you should do some pre-processing before you send it to your machine learning model. So because if you have information what you can give the model, then it's always better than to try just the model to learn everything, because to have your own brain inside the thing is usually much better than to just leave it to the model. And here are a few things which I mentioned, which you would need for optimized approaches. So you could think of, you have discrete features and you have continuous features maybe in your data set, and you would handle them, of course, separately. So maybe you want to have some some regularization on them before you send them to a method. Then what you would do, for example, for discrete features might be something like, I don't know, a better binomial regularization, and for continuous features you might use splines or orthogonal polynomials or something like that. And you have to find a way to distinguish maybe missing values which you have in your data. Sometimes you can exploit them, sometimes they are just disturbing your method. But they can contain information, of course. And you might want to have a measure of the statistical significance of your input variables. So maybe you want to leave some out to not disturbing your method in the end. This can be. So this is really important, and one should always think about it if one is developing a new method. So, but then coming to the core, so to machine learning. So this is something which basically everybody of you probably knows. So machine learning approaches just extract the patterns from the data. So that means you have your historic data, or in physics it might be Monte Carlo simulations of your Higgs boson or something like that. And out of this you want to learn how a typical Higgs boson looks like. And then you want to exploit it on an unknown data set. And in business for the future, for example, to learn from the historic data and exploit it in the future. And basically you can distinguish it into classification and regression. So a classification would be just to put a specific sample to a category. So it might be yes or no, it might be 1 or 0, and it might be 10 categories or something like that. And in the end, you want to give a probability if it's in 0 or in category 1, for example. And why a probability? So you could also just give a label in which it is, but usually with a probability you get also a measure on how probable it is, and you might also use it in another advanced method to maybe build a regression out of it. So you could build a regression model out of many classifiers, for example. If you really do it with a probability output and then combine it in a Bayesian way, then you have an easy way to build a regression model out of classifiers, which are usually much easier. So regression model is just a prediction of a quantity. So that means, for example, there might be the sales tomorrow or insurance claim, or it could be anything. So usually most of the cases which we are dealing with are more regression problems, but there might be also some interesting classification things like, for example, churn probability or something like that. I will give an example in the end of both of them. So, and another thing about it is the training methods. So there are basically two different training methods, so supervised and unsupervised learning. So as I said, so you just use historic data and with the features inside it, and you have a target defined in the supervised learning, and this target is known, and you want to build a map from input to output, so from your features to the target. And in the unsupervised learning, so sometimes also just one says clustering to it, so this means you just want to find the structures in your data and you have no target defined. Both are useful, it depends on the use case. If you do predictional models, most of the cases I would say are in supervised learning. What I said before with the reinforcement learning stuff might be something additional, so which I've not written down here again. So then, what algorithms one can use. I won't go into detail of any of those, so we can discuss later on if you are interested. But so, for example, random forest, gradient boosting. So these are things which came up in the last years, let's say, which are really good and very interesting. Support vector machines, neural networks are out there for years now. Neural networks are really old, so I have two pictures there now from a neural network, how it works. So they got interesting again only maybe 20 years ago or something, or 25 years ago, when this whole backpropagation stuff was invented. And what you can see there is how it works. You have your inputs, so your features, so which are already pre-processed, as I said. So these you feed into a model, and then you might have different layers. So here's just one hidden layer. So this are the green dots in the middle, and it's all coming to one output in the end. And in the bottom plot, you just see one of those hidden layers, for example. So one of such neurons, let's say, or the output node it could also be. And how it would work is you just define some weights, which are then going to some function, so might be a sigmoid or something, which you see there, and which are then combined to one output. So this is basically how this method works. And for the others, it's always the same. So you have to have some multivariate method which includes all your information which you have in the input, and you want to build it to one output. Okay, so what is one problem there? So maybe the most important problem you have in machine learning is the curse of dimensionality. So that means if you have many variables in your data, so then this leads to a high dimensional feature space. So what you see there is just if you have one variable, 2 or 3, and the volume of these feature spaces increases exponentially with the number of dimensions or features, and usually you have a lot of features in your data. And sometimes it happens that you have only a few samples. So if you think on a time series or something and a lot of external information you might have, then you have a lot of features and only a few hundred samples, and then it's very difficult to learn to train a machine learning model on it. So then you have to find some other ways or some intelligence to avoid such a situation. So to explain it a bit more easier, I would say you can see it here with an example where you just have 4 points and want to describe them, for example, by a polynomial. So if you have a model with enough parameters, so that means few samples and a lot of features, then you can just fit it and it works in your training data set. But it won't work later on in your prediction data set. So it's better to have a model which is not that complicated with less parameters, but which is generalizable. So, for example, we heard yesterday in this car talk, which was really great, but there we had one example where we had something which might not have this feature of generalization in it. So there we said, or it was said that one of those cars is just trained on just this specific car, so on this specific driver. So that means you can only predict this driver in the end. But what you would be interested in the end would be, of course, something like you train on just a set of a few different cars and then exploit it to make predictions for all cars in that city or something like that. So this is what I would mean with generalization. So, and this is something which is sometimes not so easy to have. Okay, so now a bit more technical. I just choose now supervised regression for it. So how a fit and a predict would work in such a method. So here you have now your inputs. So this is now for one sample, just a few different things which you could use. So maybe if you want to make a prediction for online shop for the revenue of, I don't know, a t-shirt or something like that. And then there might be an article size, a picture size, and so on. But there might be also some more difficult features in it. So you could build beforehand a time series model, for example, which gives you the information about the sales in the past. So it might be a simple moving average, but it could also be something more advanced like an ARMA model or whatever. And you just can include those information also to your features. Or you can maybe train a random forest beforehand and then put the output of the random forest inside another method. So this is something, so what you build out of your features is up to you. It can be as complicated as you like. And then you combine it in such one machine learning fit and extract the significant information, and in the end you just capture the model parameters inside an expertise. For example, for a neural network, this would be these weights of the different weights which we saw in the previous slide. And what is interesting here, of course, so this is only one sample, but you would do a fit, of course, on many samples. And for the predict, you would then do it on one sample. So that means that it might be a batch prediction where it just predict the whole data set, or it might be also some real-time application where you just get also only one sample at a time, and then you do the prediction on that. But what is interesting is that it's new data, so that means you haven't seen this stuff before. There was nothing learned by heart or something, so you really have to generalize it before, and then you would use the expertise you have trained in before, and then to give some output in the end. And what is an important point there is that the output is not just a number. So it should actually return, in case of a classification, a set, a probability. And in case of the regression, it should, in best case, give you a probability density distribution. And the reason for that is there are two things. So first of all, it will give you an individual density distribution. So that means as you do it on each sample separately, you get not, let's say, an average sample in the end, what you would get out there, which is the dark curve, but it would be an individual event, so an individual density distribution. And this is of course interesting because you are interested in the real localization and dispersion measure of this one sample and not of your whole samples. So you want it individualized. And the second point is you don't want a single number because you want also an estimate on how precise it is. So usually all these distributions are not symmetric, but they are asymmetric. So if you think on just on, as I said, the sales of a T-shirt or something, so this is somehow distributed like a Poisson distribution or something like that. So it won't be a Gaussian usually. And that means if you want to exploit more than just this one number of the mean of your distribution, then if you have such a complete PDF, then you can do something like, okay, I'm not taking just the mean of this distribution, but I would take maybe the median, or I would take maybe the 90% percentile. So it might be that you want to be pretty sure that you are not overestimating or not underestimating. So this just depends on the costs. I will come to that in a few moments. And for that, there's no other way than just predict the whole distribution. And most of the methods are not doing this. So this is something which is very important. So as I said, the costs, so these are actually the thing which you have to optimize. So you need to have a cost function, mostly defined from the customer maybe, if you cannot do it by yourself. And what you see here is in the black would be the actual prediction, and if it would be too low or too high, the costs would increase. And usually this goes more or less linearly in both directions. And the best point estimator for your prediction would be just the minimum of the cost function, of course. And because of this linear cost functions on both sides, you also have to think about what would be a good measure for the prediction quality of your method. And the usual case is the mean squared error. So this is just connected to the mean of your distribution, and this is what most estimators just give you. And this is okay in most use cases, but actually if you think on business cases, it's something not completely perfect, because doubling the deviation does not lead to 4 times the cost, as we saw on the plot before. So there are no quadratic euros, but only linear euros in the end. So, and also this evaluation would be dominated by outliers. If you have something which is far out on the x-axis, then you see the costs would be very big. So what is better is, of course, a linear method, because if you have linear cost functions, then this would be the MAD, for example. And this would be just more realistic in most cases. And it's connected to the median, which is a robust estimator. And so usually what you would choose for, if you're just knowing nothing about your method, you would probably choose the median instead of the mean. And this is also something which you wouldn't get from most of the methods if you don't give a probability density in the end. Okay, Another point which I had on what a data scientist is doing was this business development. And there it's, most of the cases, it's important that the data scientist is also able to define a use or business case. Because if you come to the customer, in most cases, I would say the customers don't really know what they want. So they want usually some cool big data application or something like that. But in the end, that it goes that it goes to production and that you can really earn money on a longer scale, then you need to have a business case which is really maybe saving the customer some money. And for that, you have to understand what is going on in that business. You have to be an expert in that domain, at least a bit, I would say. You have to understand what processes lead to the decisions on customer side, and have to see if you can actually support it. If there are data available which could do it, if it's possible for the customer to get the data, if the quality is okay for your methods, and you have to define, of course, what target would be good for a business case. And of course, in the end also, how you would evaluate the performance. Maybe you build a model, you think that it's very good, you send the predictions to the customer, but you haven't talked about the measure on how you would decide in the end if it's successful, and then the customer might come up with the MSE, and you think that it's much more it's much better to take the MAD. So this might be something which you just have to decide together with the customer what you are doing. And this would be something like business skills, I would say. So usually how such a project would go is you would have an initial data exploration. So you get the data from the customer, just bring it to your maybe platform or whatever. It might be also that you just get the data as it is from the customer and you transform it by yourself in a way that you can use it. And then you look through the data, build a first very simple model, and evaluate the results. So this is important that you not just start with the whole thing, build the most difficult model, and after a few months you try to give the first results back to the customer. But better build a simple model first, evaluate the results, bring it to a stage where it can really be evaluated, and then talk to the customer to discuss it, to see if it really generates value for him. And after that, you can have such a cyclic approach that you improve the model, do maybe more complicated approaches or whatever. And in the end, what is very important, so it should go productive, as I said. So you should find a way to operationalize it or whatever. So at least that it runs securely, that it runs maybe for weeks or months, or as long as the customer needs that service. So, and this is then also kind of also a software engineering aspect to it. So you are not writing scripts which are used one time, but you're writing really software which is there to last. So this means you need to have some coding skills, at least if you implement a model and take it to a production environment. So of course you need some coding skills for data exploration as well, but this is, I would say, a bit different. So, and the plots you see there is coming to Python actually. So we are using in our company mostly Python now, at least for the machine learning aspects. And you see there in the upper curve, this is actually the percentage growth in the last years of the different programming languages. And there you can see that Python actually had quite some growth in the last years. And just in the very last 2 years or something, this whole data science thing, when it became a buzzword, I would say, or all the data scientists came up. So one saw that also Python got much more popular, let's say. So Python is really becoming the language of choice for the data scientist. This is what one can see. And this was different in the past. So there it was mostly R, I would say, which was used for machine learning stuff, at least outside of academia. And usually what you had is this two-language problem. So that means that you had something like R or MATLAB to look through your data, build your models and everything. And then in the end, if you want to bring it to a production system, you needed something else like C++ or Java or whatever. So that meant that you had to re-implement it again, or maybe have to write everything from scratch. And this, of course, is it's expensive. It's also dangerous because your model can be wrong afterwards. So you have to check it again, and so on and so on. So usually it's good to have a language where you can just do both things, at least almost as good as you could do it with the domain-specific things. And something like this is Python. So it has a large body of libraries. a great community. You have cool stuff where you can do machine learning with. So for example, scikit-learn. You can do also web application, system programming. You are really fast for if you do just model development, and you have tools to get also performance boost for things where you really need it. So in algorithms, usually, okay, first you should of course look that your algorithm is fast. So you could have a performance boost by such a method for a poor algorithm, and it would be just stupid. So the first thing is of course to have a cool algorithm, but afterwards it might be also useful to have some methods like Sizen or NumPy where you can really just then increase the speed of Python a lot, because just as it is a dynamic interpreted language, it's just not that fast as C is in for loops or something like that. Okay, and it has also straightforward integration of external compiled libraries, which can also be very useful if you think on numerical methods or something like that. So something which came up in, I would say, the last maybe few years is really that you have data sets which are larger than your memory. So what the methods which I showed, so neural networks and support vector machines and all of those. So usually these are algorithms which where all the data which you want to train off, they have to just to fit into memory. So you have to load all the data on your machine in memory, and then you can run your method on it. So this can be difficult if you want to train on a large data set. So of course, what you could do, you could just do a trivial parallelization, let's say, that you just split your data into 100 chunks and then retrain on those 100 chunks and predict in the end again on these data chunks for the unknown data. But then you might lose information. So if you think, for example, on some rare events. So if you want to, let's say, predict some sales in a supermarket, and then there is a specific behavior before Christmas, for example, then you have only a few events of Christmas in your data set. And if you would split it up too many, you might just suffer from the case that you don't have the correlations between those variables and all the others in. So in such situations, what you want to do is you want to train on all data available, and for that you need some methods to really, let's say, not have this RAM usage problem. And for that, you need some intelligent algorithms which are able to stream, or some out-of-core algorithms. And in Python, there are a few solutions to do it. So you just have to write your cool algorithms which can do this, and then you can use the Python tools to do something like that. And the other problem is, of course, runtime then. So this wouldn't solve your runtime problem. You would still be slow. But for that, you would need to write parallel algorithms which you could then combine in the end. So this is maybe basically what is done with MapReduce or something like that. Okay, and the last point I had on the data science definition was this visualization stuff and the data storytelling. And this is just important to let the customer understand what you are doing. So to tell him a story which just convinces him that it's useful for him what you are doing. And what you see there is just a simple example how you could maybe make something like this more visible. So you have just a time series of the sales of shrimps on the Italian coast, and sometimes there are these peaks in. And if you would just overlay a calendar of it, so you would see, okay, this is always the vacation season or something like that. So this means just a simple story you would have to tell the customer that they understand what's going on. And it can be also something like that. So here you just see the prediction and the forecasts overlaid on a time series base. And there you could see, okay, so it's more or less okay, but on one specific day I don't actually know what's going on. And then you could do something like this, so you cannot read it now, but these are just the different features and how they would influence the prediction in the end. So that means this is now a multiplicative model. So that means each of the features gets a factor in the end, which would say, okay, if the factor is 1, then this feature has no influence on this specific prediction, on this sample. And here it would say, okay, this feature has a factor of 2, so this had a large influence on your model. This had the different direction and only a factor of 0.25 or something. So there you could tell the customer, okay, for this specific prediction, this was your influencing, this were your most important influencing factors. And for that, of course, you also need methods which can do this. So you need an algorithm which is able to do this. But this could be then, of course, pretty cool to convince a customer why he should use that stuff, because he could say, okay, if this is the case, then maybe my prediction or my sales is low. So now in the end, I don't know how much time I have, but to have a few real-world examples, which I promised. So churn management, I already said. So it might be something in telecommunications, or here this plot is from a newspaper contract project. So where you want to know the risk for a specific customer to cancel a contract. Why do you want to know this? Because if you know which customers are risky, then you can have some activity to maybe just avoid the canceling of the contract, let's say. So, and this would be an example of just a prediction in the first place, so that you say, I predict if a customer is most likely to cancel the contract. And what you see there is just the evaluation of such a prediction. So this is a lift chart. So you on this point, you would identify 67% of all customers which are likely to cancel their contract by just predicting, by just having the first 10%. So this means you would do an action on only 10% of your customers, because you might have only let's say marketing budget to call 10%. And if you have this method, then you would have 67% of all the cancelers inside the first 10%. So this is, of course, then good. But in the end, the question is this something which has really value to the customer? And it might have, if the customer does the right thing, the right decision out of it. But it might also be something which is dangerous, because they could just call the first 10%, and this might be people which are then maybe reminded to cancel their contract or something like that. So you should better have maybe an intelligent decision behind it to really do directly a targeted promotion or some individualized method to prevent the churn. And this would then be the way from predictive to prescriptive, actually. Another thing which I just used as example through the whole talk was this demand forecast. So there it was just maybe this jeans or something on this specific catalog for this item and for this size, and then you do a prediction, which would then be the green dot, and you compare it in the end with your truth, which would be the red cross afterwards, and if you would have something like a measure of the so let's say the variance of your prediction, then you could see if your whole density distribution makes sense, and you could say, okay, I want to be that sure that I'm not overestimating or underestimating. And here again, the demand forecast is only something where the customer would get the information, okay, tomorrow this jeans might be sold 10 times, but then still the case, is this really useful or not? So if you think, for example, on the supermarket thing, so there, if you know tomorrow, I don't know, this bottle of water will be sold 10 times, this is something which is not really useful. But if you would know you have to order 5 bottles, so this would be something which would be useful. So that means you would do kind of a replenishment after such an demand forecast. So why you would do it? Because you don't want to have too few or too many articles ordered in the end, because if you have too few, then you just lose revenue. You have high costs to maybe buy new stuff from a supplier, and the customers are of course not happy. If you have too much, then you have the cost to store the stuff, and you waste just the goods. They have to be thrown away, and this is also something which you don't know. So that means by that you can if you find the right cost function, and in the end, then you have a decision for the customers where it's not necessary for them to really find a solution out of just a number. So as a conclusion, so what data scientists are, so there are quite a few different let's say definitions of it. So they can be data hygienists. So that means you have to keep the data clean over the whole life cycle. You are a data explorer. You have to find the data sets which are necessary for your specific use case. You need to put it in a way that you can use it in your model for this specific business case. You are then model developers, which would be one definition of data scientists in its own, that you're really knowing machine learning, statistics, and so on. And in the end, you have to be a business expert to turn the models into results and into a business case. So, and as last words, so real-world data science really includes operationalization. So that means this whole platform discussion which we had. So this is really necessary, that you are not just building your R model and then afterwards you make a PowerPoint presentation and that's it. So that means the ultimate goal of it would be automated decisions, so that you really build models which where it's not necessary for the customer to think about it anymore, but you have everything automated by it. And that Python is great for data science actually. So you have tools for fast model development, and it's also suited for productive use. So, and this is also why we decided at some point to just use Python throughout the whole process actually. Yeah, and that's basically it.
Yeah, thanks a lot, Felix, for this nice overview talk. I think we have time for 1 or 2 questions. There's one in the back.
Thank you. You presented data scientists like kind of a black box where you put data in and you get a result out. But I think, shouldn't it be more like you're developing a question you want to answer together with your with a company, and then you just collect that data, create the models and stuff, and use the domain knowledge of the company to create better features, not only just extract features that are there, but combine them with domain knowledge to get even more insight. And later on, if you, I don't know, have like a few hundreds or thousands features, you want to do some selection of that as well. And I kind of missed that in there.
Yeah, so the question was if it should be, so it was presented like a black box, and it should be more like that the customer understands what's going on. So, and basically, yeah, that's true. So it depends on the customer, of course. So, of course, internally, you know what's going on, and you have your predictive application, which I have now here. So with this external factors and all these things. So, of course, you have to have the experts on the customer side included. So this is because you don't know the data as good as they do. So, and this is always the case. So you have to be in contact with them, and this is also what I meant a bit with this business development. So you need to have this expertise knowledge, and then you can include it. So you should never just use it as a black box method without caring about the specific use case. So definitely not. Yeah.
All right, so we're running out of time a bit, so maybe you can get in touch with them
just ask
after
me
the talk.
afterwards.
Okay,
it's fine.
Thanks again.
Yep.